Okay, good evening. Thank you for being here tonight. It's a bit special to have a lecture today, but we have no choice. I will recall what we have done last week. Before this, I received an announcement about a meeting about grad school seminar, which is organized by NUMI. So if you're interested, I will just give it to you. Just take a picture of it. It's organized in January something 14. Probably it's interesting for third-year students, because fourth-year student it's too late, but third-year student might be interested. Okay, so what we done last week. We defined the abstract framework for covariant derivative. Can you turn off your microphone? Okay, thank you. We defined the covariant derivative with this connection. So we define this, and it turns out that this covariant derivative gives you a vector field along a curve. See the curve. And we have also seen some local expression. So when you take a chart, you can write some formula for this covariant derivative. Now, this nabla, why is it useful? I mentioned it's for defining the parallel transport. So you have a curve, you have a vector field at one place, you can transport it along a curve in a certain sense if this condition is satisfied. This is a definition of the parallel transport along a curve. And it turns out that if you do this, you preserve the scalar product between two vectors and you preserve the norm. Or between a collection, you can transport a basis. And then this is for a fixed curve. Then we define what is a geodesic. So geodesic is a special curve where the derivative, so the tangent vector, is parallel along the curve. So you define the geodesic with a condition between the derivative of the curve and this parallel transport. And we can even write an equation, which is a second order differential equation for this geodesic. In fact, you have M equations if M is a dimension of the manifold, right? And then we move to, so now we have the notion of geodesics. This is a second order differential equation, so we know we can solve it locally in time. And we have this result, which is about, you need some uniformity in the interval where it's solved. So the statement is like this: for any p, you can find an epsilon such that all tangent vectors on the tangent plane at p of size smaller than epsilon define geodesics on the interval -2, 2. So this interval, you get it because you have chosen the size of this vector small enough. And of course, this geodesic satisfied at 0, it's at p, and its derivative is this tangent vector. Of course, -2, 2 is arbitrary, but we need it in order to define this exponential function. So we take this curve at the time 1, and we say that we define x of xp. So this is going to be a point on the manifold is the curve evaluated at the time 1. And we even did a small computation showing that the distance between p and this guy, which is also the manifold, is at a distance xp, norm of xp. And I already did this picture. The thing is, usually we put the tangent, so we have the manifold, take a point. Usually you represent the tangent plane exactly on this surface, but it would be too messy, so I move it. So we have P, here the tangent plane, and this exponential map creates a diffeomorphism between a domain which is on the tangent plane and which is star shape, and I explained what it is last week, and a certain neighborhood of the point P on the manifold. So you have a diffeomorphism between this domain on the tangent plane and a certain neighborhood on the manifold around P. And this allows us to get coordinates. So we get a coordinate system. So if I call this domain omega of epsilon, its exponential is certain domain here. And every point on this domain can be parameterized by this x1 up to xm, where this FGP as it's the standard basis on the tangent space. I introduce it once you have a chart. So this is called, it's a local parametrization of the manifold. So it's a local chart. It's called a normal chart or normal coordinate system. And it has good properties. I mentioned if you express the Christoffel symbols in this, with this chart, some coefficients are very simple. And the last thing I want to mention is that we still have 2 lectures after today, one on the 8th, don't forget it, at 6:30, and on the 15th. And on the 15th, please come because it's the last lecture also, but there will be a photograph from the one office of Nagoya University who is going to take some pictures of you. Yes. Okay, let me talk about this at the end. Remind me at the end. I want to do it. To start. So we quickly finish chapter 5, and then we move to chapter 6. So we have now this exponential map. We have the notion of geodesic, and we didn't make yet a connection between geodesics and the distance. We have seen the distance between 2 points on the manifold. You take all curves and you compute the length of this curve and you take the infimum. What is the relation with geodesics? So this is the next proposition. And the statement, you have to be a bit careful, and I will explain why. So we let C be a piecewise smooth curve. You accept that it's not smooth at a few points. So a piecewise smooth curve on the manifold, on the smooth manifold, from P to Q. So from P to Q. But satisfying a precise condition and of length D of P Q. So we assume that the length of this curve is precisely the distance obtained by the minimum over all curves. Then if you parameterize C, if C is parameterized with arc length we know what is the arc length is parameterized with its arc length. Then C is a geodesic. It's smooth and it's a geodesic. So it means if between these 2 points, you know the distance, but you can construct a piecewise smooth curve which has exactly this distance, then this is a geodesic. But be careful about one thing, the condition that the length is equal to the distance is important because you easily construct a counterexample. Just to show you. Take R2, the manifold R2 minus the point 0. I remove the point 0. It's a manifold. It's R2 minus 0. And take these 2 points. It's 0, 1. And 0, minus 1. Clearly, the distance between these two is 2. D of, let's say this is P, this is Q. D of P, Q is 2, because you can easily construct a family of curve with a length converging to 2. But there is no geodesic of length 2. So you cannot realize this distance by a geodesic. So it means in this case, there is no curve, which is a geodesic, which go from P to Q of length 2. So there is no contradiction, but it means this condition is important. So if the distance is realized by a curve, you should think it like this. If the distance is realized by the curve, this curve, once it is in the arc length parametrization, is a geodesic. Okay. If you have any question, of course, you can ask me. So minimal distance, if realized, are realized by a geodesic. Remember, the parametrization is important because if you just take a curve with one parametrization, it can be a geodesic, but with other parametrization, it might not be a geodesic. So it depends on the parametrization. And now the last theorem of this section, it's a bit technical. Still, I need to mention it because it's an important. It's called Hopf-Reno theorem. It makes a link between the different things I introduced. So you consider M a connected Riemannian manifold. Connected, remember, it means in one piece. We consider a connected Riemannian manifold, and the following statements are equivalent. There are 4 equivalent statements. Usually it's 3, but I prefer to put 4. So the following one, the first one is M, it's called geodesically complete. What does it mean? Sorry? No, not at all. Remember, I removed this picture, but we had the tangent plane at a certain P. This is Tp of M. And the condition was for this omega was of size epsilon. So geodesically complete means you don't need any restriction on the, so geodesic, exponential map defined on all TPM. So you don't need to restrict on a small domain. You can define it even for vectors which are of big length. This is a notion of geodesically complete. And very close to this, all geodesics can be extended. Be careful, extended to R mean, you remember I had an interval minus epsilon to epsilon solution of a differential equation was defined only locally. Then you can extend this domain on the entire line. And you can quite easily see that these two things are equivalent because you rescale. You rescale the vectors or you rescale the time. So this is not difficult. A third one, which is much more involved, but I want to mention it. Bounded and closed subset of M are compact. So I introduced the notion of compact already a long time ago. Every covering except open covering except a finite subcovering. It tells you that if you have your manifold and you take a bounded, this is easy to understand, and closed, we define the notion of closed, then it's compact. Okay. I told you it's. And the last thing is we have seen that the manifold is a metric space. We have this notion of distance. Then there is a notion of this metric space is complete. Again, don't worry, this statement is probably for more advanced students, I mean, 3rd and 4th year. Complete, we have seen it in different framework. Some of you know it's about Cauchy sequence. It means all Cauchy sequence converge. So if you don't remember, if you don't know what is a Cauchy sequence, it doesn't matter. It's not the... You do? Oh, yeah. Okay, excellent. So it means this manifold is good because it has exactly this property that all Cauchy sequences converge inside the manifold. Okay, so it's an important result because it gives you different characterization of good manifolds in this sense. And it has one more consequence, or two consequences. Compact manifold. And you know, when we draw a picture like this, we even always have in mind compact manifold. Compact manifold are geodesically complete, or any of the other characterizations, because they are equivalent. So it means compact manifolds are of this type. And the second implication, or the second consequences, is that in this case, so if we are in this setting, any PQ belonging to M can be joined by a minimal geodesic. I did not introduce what means minimal geodesic, but think about a sphere. If you take 2 points on the sphere, if you look at the node, there are the notion of geodesic is big circle, but you have two of them, either a small one or a bigger one. So the minimal one means like this one, which is smaller one. Yes. Okay, I let you do a report on manifold of infinite dimension. So why do you ask this question? If you cannot do it, why do you ask the question? Of course, M, when I write a manifold M of dimension M, I always assume that M is a finite number. Of course. Okay, with this, we have finished chapter 5. Do you have any question? So you should remember the notion of geodesic because they appear at many places. This statement is less important, but you should also remember that geodesic, if they exist, give you the shortest distance between 2 points. That's important. Okay. Chapter 6, it's about curvature. So I had a small problem when preparing this chapter for the following reason. I could either give you only the abstract version in any dimension for manifolds which are not embedded, but it's a bit abstract and we don't see really what happens. So finally, I've decided to do a chapter for surfaces in R3 because we are familiar and we have my umbrella. This is a surface in R3. So the first section is really on this case. I will try to go quickly, but yeah, some notions are important. And if you have any question, you interrupt me. So we consider M a manifold in R3 of dimension 2. I consider a manifold of dimension 2 and a local chart, U phi, a chart. So remember the picture, you have your manifold, and locally, this part looks like a subset of R2. This I denoted by phi, this is U. This is the image of U, phi of U. Okay, this is the chart. But now I'm going to do the reverse because phi is bijective. So I will use the notation of your report. I will use the reverse map, because it's bijective, I will call it Xi. And Xi is going to be from this set. I don't want to keep phi of u, so I will give a new name. I will give capital Xi to this domain. Yes, it's a capital Xi. I don't know how to do it. Check with LaTeX how it is. In my notes, I put capital Xi. So what I want to consider this Xi going from this domain to u. Okay, so we assume that this phi of u, which, as I said, I denoted by capital Xi, is open. This is by definition, but connected. It's all in all my pictures, they have been connected, but I assume it's not always the case. So it's not imposed at the beginning, so I impose it right now. It's open and connected in R2. And I set this Xi from this domain to u, which is inside the manifold, and this Xi is phi minus. I just change the notation because I don't want to keep phi minus 1. And it turns out that this pair is a parametrization of u. So what I'm doing, I have the manifold. Locally, this part looks like a bit of Rn. Maybe we can just take the projection. I'm taking the reverse, so from a two-dimensional space to the u. This is what I'm doing here. Okay, so it means Xi of uv, and u and v are points in this domain. Xi of uv is a point P, which is inside u, but it's also included in R3. So it's a vector in R3. It's a point, sorry, it's a point in R3. It has 3 coordinates. So we can look at it as a point x1, x2, x3 in R3 because the manifold is inside R3. So it's special. We are not in the abstract framework. Now, what about coordinate frame? Because once we have a chart, we know that we have a coordinate frame, which is a basis on the tangent plane. So the coordinate frame, there are 2 vectors because it's 2-dimensional, which I have written in the past like this, du. And E2 is phi star minus 1 of d over dv. Okay, my u and my v might be too similar. So let me take a v like this, just to make a difference. That points in R2. But with the change of variable, I can also call this psi of d over d u. And this is psi star of d over dv. So we have seen these things. These 2 vectors are define a tangent vector on this space R2, and you push this on the manifold and on the tangent vector on the manifold. But now it means we have naturally at every point 2 tangent vector, but since we are in R3, I can construct a 3rd one. And this 3rd one is going to be perpendicular to the tangent plane. So for this, I need to assume M is orientable. Assume M orientable, so it's not the Möbius strip. And we have seen what is orientable. And we choose one orientation. So it implies that there exists NP. Yeah? These are the coordinates. Ah, you're right. Okay, I have a capital U. Okay, U is always I've been systematic, sorry, but U is always a subset of the manifold. And you are right, just here, but probably it's the only place. You're right. I use small u and small v as coordinate. They are coordinate u and v in R2. You're right. And I've never used this except today.
Right, it's like a little bar on the right.
Okay, we will. Ah.
Yeah, like
No. Okay, look at the note in case there is a problem. So since we are in R3, there exists a third vector, which, so I take it unit vector, perpendicular to E1 at P and E2 at P. So we have the tangent plane at P. We have two vectors which generate this tangent plane. And I take one vector, which I take it of norm 1. It plays a role. I take one which is orthogonal to both of them. And I choose it. You always have two possible orientations. So I choose it such that if you look at the triple E1P, E2P, and the new vector NP is oriented like the standard basis d over dx, d over dy, d over dz of R3. So we take just the standard orientation. Okay. You can always take one direction or the opposite direction. So it implies, by definition, this NP is perpendicular to TP of M, because TP of M is generated by these two vectors here. So now I consider a curve. Consider a curve. So where is this curve? Okay. I consider C from a small interval to the O. Heavy do, be careful, this is a capital U, so it's a subset inside the manifold. And this is not a U, this is belonging. With, of course, C at 0, it's the same. It's at the point P, and I choose a derivative at 0 equal to xp, which is in the tangent plane. So I choose one of them, and I set, you know, this n is defined everywhere. Now I just want to look at it along a curve. So I define the map T goes to n of T, which is by definition n at a point T on the curve. Then this map is a vector field. It's a vector field just along the curve. So it's defined just along this curve. Oh. And I'm going to take a derivative because now it's a function of one parameter. So I can take a derivative. So we consider d over dt of the norm of nt. This, you can probably tell me what it is. The norm is constant. So it's 0, it's a unit vector, which means this is also d over dt of the scalar product of f on n of t with itself. Here we are inside R3, so the scalar product is really the scalar product in R3. And this is nothing but 2 times n dot of t times n of t because everything is real. So what does it mean? It means these two vectors are perpendicular. And this one is perpendicular to the tangent plane. So it means this n dot of t is inside the tangent plane. Okay, because it's perpendicular to the one which is perpendicular to the tangent plane. Okay, this is true for any t. Oh, okay, I should be at c of t. I want to be more precise. This is at the point c of t. But look, this, of course, this depends. So we have this curve. I have the vector field, which is perpendicular, and I take a derivative, and it turns out that the derivative is on the manifold. But of course, if you change the curve, it's going to be a different one. So it also depends. So observation. This n dot of t depends on, or let's take it at 0 because I already gave a name of it at 0. This derivative at 0 depends on xp, because it's a tangent vector along the curve at this point. Okay, so we are in this framework. We consider vectors which are perpendicular to the surface. We take a derivative along this curve. And now there is a theorem which is not so difficult. So I'm in this framework, and I consider the following map, or the following function. I'd call it S. It takes an element of the tangent space. So you take a vector in the tangent space, and you send it to this n dot. So you construct a curve which satisfies, I should say, in this framework. We are in the framework introduced above, in this framework. I consider this derivative at 0, because I know at 0 it's a vector here. And as I just mentioned there, it belongs to Tp of M. So we have defined a map which takes an element of Tp of M and send it to an element of Tp of M. But the way it's done, it's taking a vector which defines a curve, at least locally, and takes the derivative of the normal vector. Be careful about the construction, but still it's a map from Tp of M to Tp of M. And it turns out that the map is linear and satisfies something which is not completely trivial. You need to work a little bit, but let me tell you. Sxp, so S, choose the xp, it gives you another element of this tangent space. Take a vector which is also in this tangent space, and this is equal to xp S of yp. Think about this. This S is a linear map, and it satisfies this relation. This should remind you something. Yes, it means S can be represented by a self-adjoint or Hermitian operator, or even a matrix, because, so this is true for any xp and yp in TPM. And TPM is finite dimensional. It's a finite dimensional vector space. So what we have just defined is a self-adjoint operator or self-adjoint matrix or Hermitian matrix. It's a linear map which is self-adjoint. So it's a bit surprising, but it works. So it means S can be represented by a self-adjoint or if you prefer Hermitian, it depends what you are more familiar with, Hermitian. And what is the dimension here? It's two-dimensional, so it's a self-adjoint or Hermitian 2 times 2 matrix, once you have chosen a basis. Okay. And in a second, I will just say if you have a Hermitian operator or Hermitian matrix, you have eigenvalue, eigenvectors. So you know there exist two eigenvalues. Oh, yes. I will come back to this in a second. So you all know Hermitian matrix. Hermitian have two eigenvalues. Any question? We are dealing with surfaces in R3. The manifold from the beginning is two-dimensional. It's my umbrella. So the tangent space is two-dimensional. So it means the dimension, yeah, these elements, these guys live in a two-dimensional space, vector space. Okay. So I just keep one small paragraph in my notes because I don't need it right now. So we have to set two eigenvalues, and we call these eigenvalues. I call them K1 and K2. They are real, of course. And one is always bigger than the other one. So I decide that I call K1 the big one among the two. And be careful, it depends. Everything depends on P. So we do this construction at every point on the manifold. Yes?
Right. P of the dual vectors rather than the normal vector.
Wait. This is just a scalar product in R3. It's a subspace of two dimensions in R3. So no. There is nothing special here. And this relation, I mean, you have to prove this relation. I'm not saying that it's completely trivial, because if you think about it, it's not so easy. You are taking the normal derivative, the derivative of this vector along a curve which has this vector as a tangent vector. Here you do the same with y, and it tells you that it gives you the same number. So this is not trivial. So you have two eigenvalues, which are called K1 and K2, and of course, they depend on P. And just a remark, which is what I skip. These eigenvalues are extreme values of the following expression. You know, you can look at this for all xp in the tangent space. This is a small exercise. Xp different from 0. I can look at this. This is a real number because it's self-adjoint. This is just a real number. You take this ratio, and now you move along all xp. So probably on a circle, it's sufficient. And it turned out that the two extreme values you obtain are K1 and K2, and all the other values are between these two. I let you think about it. Okay, but it will play a certain role in a few minutes. So we have these two eigenvalues, and they can be seen as extremal values of this expression. Okay, now just for information or notation, if K1 is equal to K2, and both are different from 0, P is called, I don't know where this name comes from, umbilical point. And if they are both equal and equal to 0, it's called P is a planar point. And when is it realized? As an example, you can think about this on a plane. If your two-dimensional space is a plane, you are always in this case. And this happens for all points if you are on a sphere. On a two-dimensional sphere, all these points all have K1 is equal to K2, different from 0. And it's related to the, I think it's 1 over the radius of the sphere. Okay, this is just for the names. Okay, now we would like to have a better interpretation of these two quantities. I mean, we did a certain construction, we obtained two eigenvalues. We would like to understand it a bit better. So I call this geometric interpretation. Okay. So I still in this framework. Now I take a vector in the tangent space at P. So I just change the point of view. We have the manifold. We take one point, we choose a P. We have the tangent space, and I choose one direction. I don't speak about a curve. I take one direction. So now we have two vectors. We have one in the tangent space, one perpendicular. It defines a plane. Right? We have two vectors. They cannot be equal because this vector is perpendicular. So it defines a plane, and this plane, which is this plane like this, is going to intersect the manifold along a curve, at least locally. So this is the concept I need. We define the intersection of a plane with the manifold. Take this, the vector space. It's two-dimensional. The vector space generated by xp and np, it's a two-dimensional vector space, intersect M along the curve, at least locally, around P, at least locally. And we can parameterize this curve with the arc lengths. We can always do this. And if you do it, it turns out that C of 0 is of course the point P, and its derivative is vector xp we started with. So we can, now this is slightly different in the sense that before I started with the curve and I took the derivative at 0, it's xp. Now I fix xp and I construct a curve by this intersection of the plane, and I parameterize the curve like this. We will see at the end of the day, it will give an explanation to what are these eigenvalues. Okay. Now we consider this scalar product again, nt n dot t. You remember, this is 0 because one is in perpendicular to the tangent plane at every point. This is inside the tangent plane. So this is true for any t in a small interval. Everything is local with this construction. So I can take a derivative. Take derivative. This is something we do in calculus, implicit differentiation. We have the constant function 0. We take its derivative and we get that its derivative is Oh, no, sorry. I did a mistake. This is C dot. But it's the same. This one is in the tangent plane. This one is perpendicular. So it's still 0. Sorry. So now I take this derivative with respect to time. We have two dependents in t. So we have two terms plus nt c 2 dots of t. And of course, it's 0 because the function itself was 0. So now we take at t is equal to 0. What do we obtain? We obtain at t is equal to 0. Okay. We have this n dot at 0, c dot at 0. But what is n dot at 0? It is, oh, what I introduced before. It is this SP. I introduced it before. And what is C dot at 0? It's XP. Right? And okay, but now this was equal to 0. So it's also equal to minus n of t, n of at 0, C dot at 0. Okay. And we have seen this expression once, 2 weeks ago. In the Frenet frame. In the Frenet frame, we have seen something like this, and it was minus k of 0, and this k, at that time, I call it the curvature. So you can check it corresponds to curvature in Frenet frame. This was true. Look, everything is still on the blackboard. Oh, probably I should have, no, I shouldn't have taken an arbitrary vector. For simplicity, it doesn't change so much. I can take it off norm 1. Simply because if I take it off norm 1, this denominator is also 1. So now you can compare. This expression is equal to that one. And we said the two eigenvalues I mentioned before are extreme values of this quantity, the maximal one and the minimal one. So what do we infer? We infer that this is true for any xp, but I can also look at the maximum value and the minimum value. So I just take different vector in this space. And I ending with different curvature, but one is going to be the maximal one, and one is going to be the minimal one, and they correspond to the eigenvalues I mentioned before. So now we have the full interpretation of these eigenvalues, because the eigenvalues I told you are extreme values. So by taking the extremal values of the curvature, so this is k of 0. And how do I get this? I just change by changing xp inside TPM, all of norm 1. I just change so inside I get 1, which is going to be a maximum. One is going to be the minimum. We get two eigenvalues, k1 and k2. So what is the final interpretation? It means these two eigenvalues are extremal values of the curvature. This is the conclusion. So we gave a meaning. K1, K2 are extremal values of the curvature. The curvature at P. And in fact, they have these two extremal values are called precisely principal curvatures. So we have two principal curvatures, K1 and K2. So they are called principal curvatures at P. So the K1 and K2, these eigenvalues of the matrix I introduced, are called principal curvatures. And just final information in this section, we also set K, which is going to be the product of these two, K1 times K2. This is called Gauss curvature. And there is a second thing we introduced. So this is definition H, which is now K1 plus K2 over 2. This is called the mean curvature. So if we summarize, at every point, we have defined curvatures in any direction. There are two special directions where the curvature takes a maximal value on another direction where it takes a minimum value. They correspond to the eigenvalue of the matrix I've introduced before, and they are called principal curvature. And then if you do the product, this is called Gauss curvature. If you take the average, it's called mean curvature. In the note, I put one or two exercises related to this. This one is important. It's called an intrinsic invariant because you can transform your manifold in a certain way and it keeps the same value. I cannot present this here, but yeah, there is many things behind this. I would be happy if somebody look at what is Gauss curvature, what is mean curvature, and also if the mean curvature is 0, the surface has a specific property. So, yes?
The trace here, the trace of the matrix is the sum of that.
You are right. Yes, this is true. Now, check if it has a specific meaning. Yeah, you are perfectly right. We do the product of the eigenvalues, we do the half of the trace, but yeah, Google mean curvature and Gauss curvature, and also if the mean curvature is 0, the surface with mean curvature is 0, you would see it's important. They play a role in physics. I think they are, yeah, check. Okay, Hevido, you can do this with me.
Is the determinant.
You're right. Yeah, thank you. Yeah, with 2x2 matrices, it's still easy to find such relations. Okay, so this is for surface in R3. We have introduced different notions, and there is this mean curvature and this Gauss curvature, which play an important role. Let's look at them. Now, I spend enough time in this section about surface in R3. I'm going to come back to various curvature in the abstract setting now, which means what we have M, a manifold, a nabla, a connection, manifold, smooth manifold, it's always smooth, plus connection. And we have seen the general definition of a connection. And by the way, if M is Riemannian, by almost everybody take this Riemannian connection, because we know that there is only one which satisfies two special properties we have seen. So take this connection, the Riemannian connection. You have others, but on Riemannian, there is one which has a special property. And in this framework, we have defined the notion of T, which was the torsion. It's a certain expression I gave. And also I gave R, which was the curvature of the connection. So I gave some formula for this. Okay, so we are back in this abstract framework. The manifold is not always embedded. There is a first identity which can be proved. And I encourage somebody interested in relativity to check this. It's called Bianchi identity. If this connection is torsion-free, so it means the torsion is 0. We have seen a certain expression for the torsion. And if it is 0, and we have seen also that it's equivalent to the Christoffel symbols. The Christoffel symbols are symmetric. So you have two versions, either the abstract one in terms of this torsion, or if you look with a chart, you have seen the Christoffel symbols are symmetric in two arguments. So if we are in this setting, then there is a certain equality. I think it plays a role in relativity. That's why I wanted to mention it. I'm not sure I will really use it later, but let me mention it. So let's look at what it is. This is true for any x, y, z, which are vector field on N. So remember, vector field is on your manifold at every point you have a vector in all tangent space. So what is it? This R is precisely what we define as a curvature, but we have seen it's a complicated object and you need to apply it to a vector field. It was, I call it an endomorphism of the tangent space, endomorphism of this vector field. So when you apply it, this guy altogether is a new vector field. So it's a new vector field. So it means you take the sum of three vector fields in a very specific way, and this turned out to be 0. But this is true, you can check, and it's written in some reference book. You can check this is true if the connection is torsion-free. You have many terms, and you check at the end of the day, they just cancel. I just mentioned this in case we need it in the last lecture. And this is an exercise. But now I can look. There is another exercise which can be done. We can look. I can look at the following thing. EJ, EK, no, I should start with IJK. What is this EI, EJ, EK? Yes, when you have your manifold, we have locally a chart. This is capital U. This is Rm. We have phi. With this chart, we generate a basis on the tangent space. And this is a field of tangent vectors. So it's precisely an element, each of them is precisely an element of, it's a vector field. So at every point, when you evaluate, I just evaluate at one point, then this is a vector on the tangent space. So each of them is one vector field. So I can look at this special vector field, and as we have seen this, when we evaluate on three vector field, it's again a vector field. So we can always write it as a linear combination of some EL. And what are the coefficients? They have to depend on these three things. So these are coefficients Ri, J, K, and I sum over L and from 1 up to M. You can always do this, and simply because this is a vector field, so you can decompose it on this basis. And the exercise is, this can be expressed in terms of the Christoffel symbols. It's a complicated expression, but what we should keep in mind, we are dealing with a manifold with a connection. This connection is equivalent to a family of Christoffel symbols. We have seen, you define the Christoffel symbol in terms of the connection, but the Christoffel symbol also defines the connection, so it's a one-to-one relation. And now we express this curvature of the connection on a certain basis. Then the coefficients here, if you put everything together, you work a little bit, you can express this coefficient in terms of these Christoffel symbol. So it means this family of coefficients are expressions. It can be expressed once you have chosen a chart in terms of Christoffel symbols. Okay, I wanted to mention this because if you want to work, it's some routine computation in the sense you just need to come back to the definition and write the different things. But, okay, why I introduce this is for the next step. I told you this section is a bit abstract. We will make a link with the previous one a bit later. Now we suppose M is Riemannian. So it implies two things. It implies that we choose the Riemannian connection, I already mentioned. But it implies that we have phi, which is a metric on the Riemannian manifold by definition. I mean, we have a metric. So I can look at this. I can define an object which is in terms of 4 vector fields. So all of them are vector fields. And I want to use what I have here. So I define this as R of X, Y, Z. And how can I play with the W? I want to use one more vector field. I can do the scalar product. This is meaningful. This is a vector field. This is a vector field. You can do, or this is by definition, it takes 2 vector fields. So more precisely, if we evaluate this as P, by definition, this is phi P of this R of X, Y, Z evaluated at P, W evaluated at P, and the metric takes precisely 2 tangent vector and give you a number. So it means before evaluating this expression is an element, it's a smooth function on the manifold with value in R. So we can define this object. And this has a name. It's called Riemannian. Riemannian. It's called the Riemannian curvature. Riemannian curvature tensor. Because it takes 4 vector fields and it gives you a smooth function. Or it does. It does. I cannot I cannot exchange so easily these things, but there is an exercise and there is some symmetry. So you can play a little bit, exchange some, and you have some relations. So this R of X, Y, Z, it's a good remark, X, Y, Z, W has some symmetries. And you can look at, there is an exercise which gives you these symmetries. I had a problem when I look at the literature on this because usually people do not write vector field, they tensor field, they just write tensor. And it makes a difference. And you know why?
Different meaning.
No. But, and this is, Chutai, this is a report for you if you haven't done something. There is a small trick which is very nice, but not easy. I mean, no, it's not exposed everywhere, so it took me a while to find a place. So as I said, in many places, they do not write vector tensor field, and you can also, you can see in books the following expressions: R of XP, YP, ZP, WP. And then you say, oh, there is a problem. Because, okay, these things are complicated, but you need to put vector fields. And it's a vector field is a function on M with value on vectors, while here you just put vectors. And if you come back to many of these expressions, you have derivatives. And if you just look at a value at one point, you cannot take derivative. So there was something strange. Probably, Chris, you know the thing. So really, you can see in the literature, people wrote this, and they just call it the Riemannian curvature tensor, not tensor field. And there is a reason. So this remark is important, and in the notes, I put a reference. It turned out that, so it is in this remark. We already mentioned the map. If you take X, Y, Z, goes to R of X, Y applied to Z, we have seen that is C infinity of M linear in each argument. I don't know if you remember the meaning, but it means, of course, it's linear in each argument, but C infinity of M linear means if I put a F here, I can always rescale the vector field. If I can put a F here, it's the same as taking it outside in each argument. So it's not only linear, but you can multiply on the left of each entry by a smooth function on M, and you can take it outside. So it's linear in each argument, C infinity of M linear in each argument, and similarly, Now, if you make it even more complicated, if you look at 4 arguments, x, y, z, w goes to what I define R of x, y, z, w. So you already know that it's C infinity of M linear in these 3, but it turns out that it's also C infinity linear in this one because of this scalar product or metric. So this is C infinity of M linear in the 4 argument. This is the first remark. So we have not only linearity, but this very strong version of linearity. And there is a theorem which tells you that if you are in this situation, a vector, a tensor field is also a tensor. So in this case, they exist. So in this case means when we have this infinity of M linearity, there exists a tensor, which is not a tensor field, which I'm also going to denote by R. So same notation. That's why it's a confusing same notation. So that we have the following equality. R of x, y, z, w evaluated at P, it's a C infinity function, so I can evaluate at P, is the same as R of xp, yp, zp, wp. And it's quite deep, if you think about it, because we first had functions, and now it means you don't need to look at this, even if these functions were only known on a small neighborhood around P, when you have this property, you don't even need to know more than just at P. And so people are using the same notation for this one, which is a tensor field, and this one, which is, you put some vector, so it's just a tensor. So it's a rather, yeah, there is a proof for showing that when you have this property, you have this. So don't be surprised if in the literature you find Riemannian curvature tensor and not tensor field. I added, in fact, this field because this is the first way you see it. But then once you use this result, you have this. So I'm going to use this result with the same notation. But in order to do it, you need to have this infinity of M linearity. If it is just R linear, you cannot do it. OK, it's a long remark, but it takes a while to clarify it. OK. So if we summarize, we had the notion of curvature of a connection. It has a certain definition. Then we have seen Bianchi identity, which when the connection is torsion-free, you have a certain equality. And the next step is we define something with 4 vector field. It's meaningful when we are on a Riemannian manifold because we have the metric with phi, the symmetric tensor field. And OK, I've defined something. Now I want to come back to 2 dimensions. Of course, we are in a space in higher dimension, but I can still come back to 2 dimensions in the following sense. Now I consider, and I use this letter pi, I consider a subspace 2-dimensional subspace. So you have TPM, which is of the dimension of the manifold. Unfortunately, my manifold here is two-dimensional, so it means the tangent space is two-dimensional. I cannot construct anything else as a two-dimensional subspace. But think about a manifold of dimension 3. The tangent space is three-dimensional. And inside this three-dimensional space, you have plenty of two-dimensional subspace. These are called, they are called plane section. And I'm going to play a bit with this plane section. When we consider two vectors, xp, yp, inside TPM, generating this two-dimensional subspace. So I consider two vectors in this space of dimension m, and I assume they generate this subspace. And I said something. K of pi, and it will already tell you something, or it already tells you something. Define this R of xp, yp, xp, yp. Heavy do, yes, the order is important. So xp, yp, xp, yp, and I divide by phi p of xp, xp. I take the complicated version. I will simplify it in a second. And please be aware, I'm using what I just mentioned before. Otherwise, the right-hand side has simply no meaning because I evaluate everything at one point. So I need to use this fact that there is a tensor, not only a tensor field. So I define this quantity, which is R I have introduced, evaluated at xpyp, xpyp, and I divide by the norm of xp square, the norm of yp square minus the scalar product between these two. Okay. And as you can see from the notation, it turns out that this quantity depends only on the subspace and not on the choice of xp and yp, which is not completely trivial. It means if you take another choice of xp, yp, you can take linear combination of these two, you end up with the same value here. It's not trivial, but this, you need to use the properties of R, this R of 4 arguments. And in particular, if you take xp and yp of norm 1, this is 1. And if you take them orthogonal, you can always take them orthogonal with a scalar or inner product given by phi, you have just a numerator. So you have 1 minus 0. So a special choice is to take an orthonormal basis, and you have just a numerator. And this is called, this K of pi is called the sectional curvature. The good point is it's a simpler object because it's only related to a two-dimensional subspace. It does not depend on too many things, it's two-dimensional. And it turned out that there is a theorem, I don't want to insist because I'm not sure we will use it, but the Riemannian curvature tensor, which is this function of 4 arguments, is uniquely, or at P, we should write at P, at P is uniquely defined by all sectional curvature. So it means this object which depend on four variables, it's completely defined if you have all sectional curvature. So it means you take all different planes. Of course, it's a big collection because you have to consider all planes in your space Rm, but it's a certain result. And now just for some definition, the manifold M is called isotropic at P. It's called isotropic at P if this K of pi does not depend on the choice of pi. So what does it mean? It means in your m-dimensional space, no matter which two-dimensional space you take, you get the same thing. And we will see in a second, if we are back in the two-dimensional space, it makes sense. So it's called isotropic at P if it doesn't depend on the subspace. It's called isotropic. Is isotropic if, and is isotropic if isotropic at all P. So if you have this property not only at one point but everywhere, it doesn't mean they are the same at every point, but you have these properties at every point. It isotropic. If it is isotropic at all points, and then M is of constant curvature. Constant curvature if K of pi is the same everywhere. And now what happens if M, or if the dimension, if M is 2, of course it implies that the dimension of TPM is equal to 2. So in this case, you have only one possible subspace of dimension 2, it's the space itself. So it means M is isotropic by definition at every P. So the first of these conditions is always satisfied, and then it's isotropic. I mean, it's even, yeah, then it implies that it is isotropic. Because you have this property everywhere. And there is just some of them will be of constant curvature if this value is the same everywhere. And you can check on internet. So manifolds of constant curvature, two-dimensional manifolds of constant curvature play an important role. So two-dimensional manifold of constant curvature are important. In the following sense, you can check that depending if k is bigger than 0, smaller than 0, or equal to 0, which is a triggered case, they have different properties. So if we summarize, we gave a definition of this k of pi in the general case. Then we gave a definition of what means isotropic at p, isotropic globally and of constant curvature for any dimension. But then in the dimension 2, of course, it's isotropic at every point, and therefore it's isotropic. And in the special case of constant curvature, they play a role. And one more remark, this still in dimension 2. So we have P of pi it's related to something we have already seen. Which I should write, which depends on P, on the point where we do it, is nothing but the Gauss curvature. I defined before Gauss curvature. You need to check that indeed the two definitions coincide. But it means we define this in the general framework, arbitrary dimension. Now, if we are back to 2 dimension, first, you can forget this because you have only one subspace. It is the subspace, the tangent space. But still, it depends on P, but it's equal to what we call the Gauss curvature at P. Both depend on P. So it means we have generalized the notion of Gauss curvature, because when you come back to 2 dimension, you recover it. But the sectional curvature is defined in any dimension. Okay, probably, yeah, what is just the next step? But I need to define what is the Ricci tensor, which is a contraction, and then the scalar curvature, which is also contraction of what I have introduced. So this is easy to define. I will just do it next time at the beginning. So probably this section is quite abstract in the sense I define different things. They play a role in relativity, so they play a role later. So what I decided to do, I illustrate with 3 dimension or manifolds of 2 dimension in 3 dimension in section 6.1. In this section 6.2, I mainly gave some definition. We have seen the difference between tensor field and tensor. So please, it's important to realize it's not automatic, but with one property, this C infinity of M linearity, you get it. And then a few things, this sectional curvature, which depends only on space of dimension 2, and a few definition. And then this corresponds to the generalization of Gauss curvature. Okay, so I will finish this next time and probably introduce still something for this chapter. On the last lecture, I will mention a little bit about general relativity, but just an epsilon. So it's Christmas, so I have some biscuits and some chocolates. So please help yourself. At least there are 2 for everybody. So please just take it. And we meet again on the 8th. We meet on the 8th, so don't forget to come. And then the last lecture is on the 15th. And don't forget to send reports. I haven't received so many recently. So some of you should feel guilty. Okay.